Alright, so now I'm going to talk about the actual practical part of the experiment, which is stuff that you're going to need to run this experiment today. So you're going to start with running a reaction that produces your CO2, and in this case you're going to mix an acid and a base, really HCl and CaCO3. The carbonate here is a base. When you run this reaction, it's a double displacement reaction. You're going to produce H2O and CO2 as part of the product. And the CO2 is what we're going to collect in this case and then use for our measurements later on. Now, a couple of reagents you're going to need is 6 molar HCl, and then you're going to have a solid here, which is just limestone, which is calcium carbonate. And when it's mixed with the HCl, it becomes aqueous, and then the reaction happens. So here's how the setup looks like. Okay, you're going to need 2 Erlenmeyer flasks, which you can get from your locker. I'm going to label this one flask A and this one flask B. Flask A is where the reaction is going to happen, so your HCl and your limestone will go in here. And then flask B is where you're going to collect the CO2. Let me just first point out the setup here. So you want to make sure that the whole thing is set up this way before you actually mix the two reactants together. Okay, so flask A would be connected to a stopper that is attached to something called a thistle tube. That is already provided as part of your equipment in the lab, so you'll see it somewhere lying on the instructor bench. And then the thistle tube has a little tube that goes sideways, which has a stopper on it. And what you're going to do is you're going to connect that to something called the drying tube, which looks like this, and connect that drying tube to the stopper. And then the other end of the drying tube, you should get a rubber hose, and then put that rubber hose and connect it into flask B. So this is the entire setup of the reaction, and then get a little aluminum foil to cover flask B to make sure that the CO2 doesn't escape the flask while you're collecting. Okay, again, this has to be done before you start any reaction. Now, what you want to do then is you want to take the flask A at this point, put in some limestone here, weigh some amount of it as instructed by your lab manual, and then connect that thistle tube again on the flask A. Okay, the thistle tube actually looks like this. There's a little opening at the top, and what you can do is you can pour your 6 molar HCl through the thistle tube, and that would cause the HCl to come down here, react with the limestone, start producing CO2. The CO2 would then travel through the tubing, the glass tubing right here, goes through the drying tube, and then goes through this tube and then gets collected in flask B. Just a quick note here, the drying tube actually a lot of times would be a little wobbly if you don't secure it somehow. So what I would suggest is get a clamp and put it on a stand, and that clamp could then be used to clamp down the drying tube so it doesn't move around. Now, there's a purpose to this drying tube. The drying tube contains basically compounds that would trap water. So the water is going to travel through the drying tube here, and then water is then going to be trapped inside the drying tube so it doesn't contaminate the CO2 gas that's collected. Remember that water is one of the products of the reaction, so that's why we need to make sure that the drying tube is there. Okay? Now let's ask the next important question about this experiment, which is, when do I know that I have to stop collecting the CO2? CO2 is a gas, it's invisible to our eye, so we don't really know when the CO2 is actually completely full inside the flask. Okay, so think about how exactly you would have to figure out that your flask is full with CO2. Well, the only way you can do this is you can do it by mass. Okay, so if you think about filling up a flask with water, for example, and let's say you can't see the water. Let's say you're blindfolded, right? You're blindfolded and you're filling this up with water, for example. So at the beginning, maybe you fill up about a third of the flask with water. Okay, so you're blindfolded, so you can't tell that it's a third full with water. But what you can do is you can sort of put that flask on your hand and sort of feel the weight of that flask at that point. And then you can fill it up again with some more water. Now, then you can put it again on your hand and then see if the mass actually is increasing the second time around. If the mass increases, you know that you've just put in some more water, which means that the flask is not yet full, because if it's full, you wouldn't be able to add any more water to it. Now, there is a point when you add more water and then you weigh that flask on your hand and you don't notice any difference between the mass before the last addition of water and after the last addition of water. That pretty much tells you that the flask is full because there's no difference in the weight of the flask before and after the addition of water. So we're going to use exactly the same concept to figure out whether our CO2 is completely filling up our flask or not. So what we're going to do is we're going to let the reaction go for 20 minutes and then we're going to weigh flask B. That's our first mass measurement. And then we're going to let that reaction continue for another 15 minutes. Now, you obviously have to be really careful. When you take that flask at the 20-minute mark and you take it to the balance room to weigh the flask, you have to make sure that the aluminum foil covers the flask so none of the CO2 is lost as you walk from your bench all the way to the balance room. Now, when you bring it back, you want to let that reaction continue for another 15 minutes. Now, the idea is exactly just as I explained it earlier with the filling up the flask with water, right? So if the difference between the mass after 35 minutes is less than 0.005 compared to the mass at 20 minutes, that pretty much tells me that at 20 minutes I basically have my flask full, so waiting another 15 minutes to fill up that flask hasn't really changed the mass, so that tells me that the flask is pretty full at that point. Now, of course, it's possible that the difference is bigger than 0.005, in which case it tells you that the flask is really not full at that time at 20 minutes, so you've just added quite a bit more of CO2 into your flask. So if that's the case, what you have to do is you have to bring the flask back to your bench, run the reaction for another 5 minutes, and then measure the mass again. And then take the difference now between the mass at 40 minutes minus the mass at 35 minutes. If that difference is less or equal to 0.05 gram, that means you're done. That means that the flask is full at that point because there's no more huge change in mass. If it's not done yet, then you have to repeat this for another 5 minutes and just keep repeating that until the difference is less than or equal to 0.05 gram. A couple of things that I want to point out that's really important. You have to make sure that that flask B that you use to collect the CO2 is dry at the beginning. Sometimes people see that there's a little bit of water that's in there at the beginning and they didn't clean it up. As the reaction progresses, that water might evaporate, in which case your mass measurement would be affected by the evaporation of the water and the filling in of the flask with CO2. If this happens, your data would be have a huge error when you're calculating the molar mass of the CO2. So just make sure at the beginning that your flask is dry. All right, the last part I want to mention about is the measurement of one of the masses. Most of the masses that you're going to measure for the flask containing air or containing CO2 would be done in the balance room using the digital balance. However, there is a part where you have to measure the mass of the flask when it's completely filled with water. That measurement has to be done with the triple beam balance instead of the digital balance. The reason is because the digital balance actually can only accommodate a certain amount of weight. And when you fill up your flask with water, it's just way too heavy for the digital balance to give you a precise reading. So what you want to do is use a balance that can accommodate that mass, and that would be the triple beam balance. Last thing I want to point out is a lot of times students forget to put the foil that they use to cover the flask during the measurement of the water. Remember that the foil is part of your mass, so it has to be subtracted out. So make sure when you're measuring the mass of the flask with water in here, you also include the foil somewhere along on the triple beam balance. Now, the triple beam balance measurement and how to use it is something that you've learned before, but you might have forgotten. So in lab, while this is going on, you can ask me to show you how to make this measurement, or you can look online to look at a video on how to use the triple beam balance.